we have a very interesting talk tutorial from Priyank Shukla called Electro-optical and Die-to-Die Interconnect Technologies in Data Centers, Significance, Advantages, and Future Implications. I'm very excited about this one. Why don't I just introduce Priyank. So he has over 15 years of experience in the semiconductor industry. He's an ASIC IP product manager who has managed and driven complex product development cycles from concept to release. Currently, he serves as senior staff product manager of interface IPs at Synopsys Incorporated. In this role, he oversees a portfolio of products that include 112G, 224G high-speed SerDes, 400 gig, 800 gig, 1 terabit Ethernet, PCI 5 through 7. He's also IEEE 802.3 working group voter contributor and to the IEEE 802.3 task forces. So very impressive bio, and we're excited to hear all about this topic. Thank you, Priyank. Take it away.
Thanks, Dave. I'll shut down my video to save bandwidth from here. There seems to be some connectivity. And then for Q&A, I'll come back and then I'll start my video. So thank you so much for the great introduction. So as you said, I have been involved with high-speed interconnects for last 16 years almost now. And I started my career as analog mixed signal design engineer. As a design engineer, my last design was 25 gig SerDes, serializer, deserializer. And now I'm managing the team and products for 224 gig SerDes. So it's really great to be talking with the Hot Interconnect community today. It's my first time presenting at HOTI, and I'm really excited to interact with the team. So as we discussed, there are a few people who joined a minute late. So for everybody's interest, so this tutorial will be segmented into 2 sections. First section will be about an hour, where I'll talk about electrical and electro-optical interfaces in the data center. Then we will stop the tutorial for about 10 minutes, and I'll take questions there. Then we'll go with a 5 minutes bio break, and then we'll resume and focus on the second section, which is for die-to-die interconnect technology. That will again run for about an hour. So there'll be ample time for questions. Feel free to type your question as and when they come in the Slack, and maybe you can write the slide number as well. So once we take those questions, we'll be able to come back to the slides. So with all that logistics taken care of, let's start with today's tutorial. And here's the agenda that I'm planning to cover. And this in turn will address the points we were trying to cover about the significance of this interconnect and what's happening now, what's planned for future. So we'll start with a system level view of data center architecture. There have been a lot of great presentations here in this conference and previously as well. But just to bring everybody onto the same page, I'll start with the architecture from the system level point of view. And then we will deep dive into different types of architects of interconnects in the data center. So there are 2 different types of interconnect I want to first focus on. One is the type of interconnect that can be a memory mapped IO type of interconnect, which is sort of PCIe and CXL. So I'll always use this abbreviation. So I have expanded first time. This PCIe is a standard from PCIe SIG. It's been about 20 years. The standard has matured from being a parallel interface. It was called PCIe only, no express, way back in 2001. And now it's in 6th generation PCIe Gen 6, which goes for 64 gigatransfer per second. And there's another architecture called Compute Express Link. And we'll talk about that. Currently, the CXL 3.0 is in deployment phase, and people are talking about CXL 4.0 as well. So we'll talk about these 2 protocols and why they are important. We'll touch a bit about the protocol part, then we'll talk about the electrical, because this talk is going to focus on the interconnect technologies mainly. Then the second class of interconnect technologies, which are Ethernet and InfiniBand. So these are packet type, best effort, networking interconnect technology. So we'll see the protocol stack for this kind of technology, how they are different from memory mapped IO kind of PCIe Express and CXL. And then we'll talk about the electro-optical interfaces and how they are migrating from present implementation of pluggable to something which is called non-retimed or linear or analog drive. There are many different names. So that's what being currently discussed at different standard bodies, and it's going through implement phase. So we'll talk about this migration in terms of technology progress. And second mega trend we are seeing on electro-optical interface is this pluggable interfaces are paving the way for co-packaged optics, CPO, and also near packaged optics. So the difference between these two technology is in co-packaged optics, the optical die, which has the trans impedance amplifier and photodetector, TIA and PD, is on the same package as electrical die. Whereas in near packaged optics, the optical part is connected to the electrical die on a PCB. So it's not on the same package. But this is a very interesting development in terms of the deployments of optics in the data center. So this will be our first section. And then we will take a break and then we'll switch to the die-to-die interfaces section. And there's a lot happening here. The two different types of die-to-die interfaces that are currently being deployed and talked about are a serial-based interface, which is called XSR, extra short reach. So this is a die-to-die interface proposed by OIF, Optical Interconnection Forum. And this is a SerDes technology, serializer and deserializer. And it's about 56 gig and 112 gig. And there are talks of 224 gig today. So that's the SerDes technology. And the second is the UCIe interface, Universal Chiplet Interconnect Express. And it's a parallel die-to-die interface. And currently there are talks of 16 Gbps to 24 and 32 Gbps per pin throughput for this UCI technology. So we'll talk about those. So that was very brief introduction, and let's get into the first section of this tutorial, which talks about the data center. So I have taken a very broad definition of data centers. Data center could mean many things to many people. It could mean on-premise compute facility. It could mean a cloud-based compute facility. It can be classified into a traditional or modern data center based on physical layout and design. But this slide provides a conceptual understanding without digging deep into the different types of compute it can offer. So this shows an example of a cloud-based data center where the users interface through ISPs, Internet Service Provider. For example, today, when we, let's say, go to Amazon's website and we open a page, we just make one query through our Internet Service Provider to Amazon server, which will sit in one of the data centers. But that one query at Amazon.com gets serviced by multiple servers or accelerators, which are interconnected through different switches. So there are different types of switch topologies. So these are generally used term in the industry, spine, leaf, and top of the rack switches. And what it essentially means is the servers will be part of a rack unit. So this picture pictorially shows a rack of a hyperscale data center, which can be considered as a building block of data center. So one rack has multiple rack units, and there could be different compute or memory resources in those rack units. So in these data centers, those compute memory interfaces are connected through different channels. And we'll talk about those interconnection and different types of protocols or standards going forward. But at very high level, there are multiple interconnects that connects that server. And then the one server, let's say, resides in this one rack unit, and that addresses our query to Amazon.com, which shows, let's say, recommended products. But there would be another server which might sit somewhere else. And based on our previous search history, it will suggest you might be interested in. So the one query which we made to Amazon.com server through our ISP goes through Amazon data center. And then it starts one query to, let's say, this rack unit, and then in turn, other query to another rack unit, whether to be an accelerator which will provide an output. And all these are combined together and then rendered as a web page to our browser. So this was talked a lot in last 10 years when cloud-based data center started their deployment, that the traffic from ISP to the data center it's creating 15x to 100x more traffic within the data center. So one query from one user creates so much interconnect traffic. So that's the point I was trying to make. And other point is there are some workloads. So workloads are the problems that data center compute facilities try to solve. So it could be just unstructured data that gets processed in a lot of accelerators or machine learning GPU resources in some part of data center. So even to process that workload, there are a lot of back and forth between the data center interconnects. So the interconnects are used very widely. Now in 2023 is well established that the total power in the data center is driven by the interconnect power, because one query is generating a lot of responses and a lot of interconnect. So the idea here is to just show the structure of a data center, cloud data center, and we will focus more into HPC data center or high performance compute. So within the data center, there is a segment of compute facility which is just designed to process workloads for, let's say, machine learning and large language model. So what's special there? What kind of architecture exists to address that HPC problem? We'll also address. But this gives us understanding that in a data center, you have about 10K switches. So those will be different types of switches, will be top of the rack, then leaf and spine. So all this together in a greenfield data center, there are about 10K switches of different throughput. Let's say this top of the rack will process at 3.2 terabit per second. I'm just giving some number to understand the scale, but because leaf and fabric connects multiple 3.2 terabits throughputs together, so you might need a 12.8 terabit per second switch here. And then spine, you might need a 50 terabit switch for implementing this kind of class architecture. So there are different types of switches, and switches differentiate themselves based on their reach. We'll talk about that again. But at very high level, to make a data center, you need about 10K switches. And then there are about 100K. So this just shows the rough order of magnitude. Then you need 10 times more servers and accelerator. So the recent term that a lot of people are talking is one query to ChatGPT gets processed by 8 GPUs. So there's so much servers and accelerators that are needed in addition to switches. And finally, there are about 1 million optical interconnects that connects the server together. So this gives an idea of the scale of different types of interconnect needed in a modern data center. And this is a public news that different hyperscalers have 4 or 5 years of replacement cycle in their data center. So every 4 or 5 years, these all elements will go through their upgrade. So the data rate changes. So we are talking about this problem where interconnects solve a bigger problem, and optimizing those interconnect and designing them better will have a real differentiated performance. So that was this slide. And now this slide tries to address the question why interconnects are important in data center. People talk at high level about switches or optical module, but why specifically we need to talk about interconnect? So there are many reasons. I can provide whole level of empirical reason that the data transfer and communication, server to server communication, storage connectivity, virtualization, all these are driven by interconnect. But instead of citing those empirical reason, I have two key reason or the quantifiable metric to make my case why interconnects are important in the data center. So today, the data center electricity use, this is an estimate by IEA. It's International Intergovernment Energy Authority. So there are 31 members to it. It's based out of the US, and its member contribute 80% of total energy consumption. So they have visibility into 80% of worldwide energy consumption space. And this is prediction from them for the last year. that in 2022, the total data center electricity use was about 240 to 340 terawatt hour. So it's about 1.5 to 2% of worldwide energy generation. And this is on an average energy consumption of countries such as Iran, which is 13th most populous country in the world. So now the data center alone are contributing so much energy. So if we are committed to a greener future, it's very important to reduce this energy. So that's the starting point. Now let's look into where this energy is dissipated. So there is a metric called power usage effectiveness, or PUE. This is a metric all the major data center deployers or implementers quote publicly. And what at very high level shows is out of total energy burnt or utilized by the facility, what's the fraction that is used by real processing? So heating and other cooling, let's say ventilation, those energy overheads are shown on top of 1. So from this, you can see that it's only 6% to 12%. It's on a basis of 1, so 0.6 is 6%. So from 6% to 12% is the additional power which is burned to maintain the data center facility. So the low-hanging fruits to save the data center power are already plugged. So those plugs have been holed. So what we need to focus now to save power is to save power in real data center processing. So now next two data points is based on our experience with these technologies. So Synopsys has been working in these technologies for more than 20 years. And what we have come to understand is the interconnect power contributes to 27% of total data center power. So it's just interconnect. Processors contribute about 20%. So if we were to save this power, 27%, we would save the overall power consumption by a fourth. And the interconnect power in the last 10 years itself have increased by 23%. So to plug the biggest hole today is to talk about interconnect power and try to minimize that. So in terms of our day-to-day experience as a SerDes or semiconductor engineers, when we talk about power, we talk about this metric picojoule per bit, or it's the same metric milliwatt per gigabit per second. So it's the energy here when we talk about picojoule per bit that is burnt to transfer a bit from one place or one chip to another chip. So that's the power efficiency we talk about. So if we save 1 picojoule per bit in our design, we are talking about saving hundreds of megawatt in a data center. So that's the scale we are talking about. So in each interconnect, we need to look deeper and try to save power. So that's the first point. So if you dig deeper into contribution of power in the data centers, it boils down to the power which is burnt in the interconnect. So that's why it's important to talk about that. And second is compute throughput. So now there are different architectures that are being tried in data center to process different kinds of workload. And the efficacy of those architecture depends on the type of interconnect we use. So we conventionally believe that the speed of light is really fast, but the point I'm making here is speed of light is slow. So we all know it's 3 into 10 to the power 8 meter per second. So if we have, let's say, 100 meters of optical interconnect, it will take 330 nanosecond for the light to travel for this 100 meters. If you compare it with the latencies we talked today from compute element to DRAM, those latency are of the order of 40 nanosecond to 80 nanosecond. So the modern workloads for large language models need a lot of processor or compute to memory interconnects, and the latency there should be less than 100 nanosecond. So we need to focus into interconnects, which will not utilize light, but copper, so that the time taken for a bit or a information to go from processor to memory is not so high. So today, to solve two biggest problem, which is power and the compute throughput, the interconnects are important. So that's the case I have for this interest.
咱一会儿出去走走，行。 一会儿咱出去走走。
Can we please mute everyone? Oh, figure out who it is.
All right, so let's look into the interconnects in a bigger detail. So previously I just talked about at very high level. Now in this slide, I'm showing the top view of different rack units. So I just highlighted this is, let's say, a rack unit, which is a compute rack unit. So from the top level, at very high level, these are the elements that in a compute rack unit, you will have a processor or an accelerator. There could be many type of accelerator. It could be GPU, it could be FPGA, or it could be a NIC. A lot of NIC as well do acceleration. But this just goes on to show that you have a processor chip or which invariably uses PCIe. So PCIe or CXL today is the de facto interconnect from a processor to a networking chip. So here I'm showing a simplistic implementation where the processor goes through a network interface card. So let's look into the different interconnects a NIC has. So the NIC has to connect with the processor through a PCIe or CXL link. So that's your one interconnect. And then on the other side, this NIC has to pump the data out through a cable. So as you can see, from a rack unit, you go to the top of the rack using cable. So there are different types of cable that are currently used. Here I'm showing a direct attached copper cable or DAC cable. So this just means that it's a copper cable and you use a pluggable module to connect that to this rack unit. So this is called faceplate of a rack unit. Typically there are 32 rack modules here, and you can connect, let's say, a direct attached copper or active optical cable. So here I'm just showing all the copper interconnects to top of the rack, but it could also be an optical interconnect. So in that case, in the same faceplate pluggable module, you will use an optical module. So I'll show how an optical module looks and the components of that optical module. But at this point, the point is we have one interconnect PCIe, and now we are talking about the second interconnect, which is Ethernet at this case. It could be InfiniBand. I'm not picking and choosing between two protocols here. I'm focusing more on electrical. So now we are talking about a packet-based protocol, and there's another interconnect we are talking about. Now it goes through a switch or the top of the rack switch. And there a lot of times based on the reach. So based on the total loss from this NIC driver. So the NIC here will have a serializer or deserializer because Ethernet and InfiniBand both are SerDes based technology. So we are using an interconnect to serialize and deserialize on the other side. And based on the channel loss, we might need a retimer. So it's another chip. It's an industry in itself to provide retimer to increase the reach of interconnect. And a lot of top of the rack switch rack unit implementers use retimers to just make sure that there's enough driving strength from all the rack units to the top of the rack. If that implementation is selected for top of the rack switch, then you have a retimer here. And now we are talking about two interconnects again here. So the retimer just improves the quality of the signal, or in the technical terms, you can say signal integrity or the reach. And on one side of this, there's an interconnect which will drive the direct attached copper. So it's both ways, right? It's a duplex. So there's a data flowing from rack unit to top of the rack and also from top of the rack to rack unit. So we are talking about full duplex interconnect here. And this will drive, again, the twin-X copper cable, or it could also be optical. But now on the other side, we are talking about driving PCB. So this is a printed circuit board channel we are talking about, which in modern day are implemented using Megatron 6 kind of substrate that has low loss. But again, we are talking about losses of 20 dB to 36 dBs. So there's another interconnect here. And then the switch is nothing but multiple interconnect, which takes packet from one side, does some buffering, inspection and some intelligence telemetry about it, and then pushes to the other side. So now we are talking about a plethora of interconnect here, because the switch will connect to all the pluggable modules here, and then maybe a retimer on the other side, so which is another interconnect, and then an optical module, because this top of the rack switch will connect to the leaf or spine switch I was showing here. So we just came till here. From here, it will probably go to an optical module, to a leaf fabric switch, and we'll go to another one. So we are talking about 1, 2, 3, 4, 5, and 6 interconnect from one processor packet, which has to pass to go to the other processor, and the number times 2 if you are making a hop. So we have to optimize this PCIe or CXL kind of links, which are used for memory mapped IO, where you can directly address a packet and you can process it. And also we need to optimize the interconnects, which are used for this networking technologies, which could be Ethernet or InfiniBand. And finally, we need to optimize this electrical to optical IOs to save overall power. So those are the broad themes of this tutorial we are going to explore and their specific use case. So this slide focuses on two specific architectures in the modern data center. So on the left side, I show a generic data center architecture. So this is not focusing on high performance compute. It is to do processing at different level and serving the queries for, let's say, rendering a web page or processing some information and doing some edge inference. So to implement that kind of data center, what is traditionally deployed is what is called converged architecture. And the hallmark of this converged architecture is you accumulate different network elements in one rack unit. So as you can see here, and this is what we have been talking about. We have been talking about this converged architecture, where each rack unit will be serving a specific purpose and will be connected through multiple levels of switch, which is called top of the rack switch. So these are my poor implementation of copper cables. So this is the same scheme we have been talking about, that each rack unit serve a purpose, and from the top of the rack switch, it will be connected to other switch. So you will see a lot of storage element here. So a lot of times let's say you're going to a site, some pictures have to be rendered. So those pictures are generally on different storage server rack unit. So to process any information here, the network becomes a bottleneck, meaning any information has to pass through multiple hops, and this is what we have been talking about. So this was one problem, and we sufficiently addressed this. The second problem in the compute, which we need to solve, is high performance compute. And this is about processing all those unstructured data through different models. So large language models is what everybody is talking about. At a very high level, what it means is there are so many parameters, billions of parameters, that needs to be processed and saved and used together. So from interconnect terms, we need to have the interconnects which connects all this CPUs and GPUs together, and they are coherent, meaning what the CPU or GPU is processing from his memory, other GPU and CPU should also have same access, because all the GPUs and CPUs together are processing one big data and working on billions of parameters together. So here we need to have memory coherency. So here the interconnect becomes the bottleneck. So today, hyperscale data center or the data centers in general are trying to address both this problem, and we are trying to address network bottleneck and also interconnect bottleneck. So let's look into each of these. We spent some time on this earlier. Now let's look into this disaggregated architecture and what is this interconnect bottleneck and why everybody is trying to process this large language model and what's the problem they are facing. So the problem for last 3-4 years have been described as a memory wall. So the problem here is not the compute cores, but the access to memory and coherency is memory. So to understand this problem, let's start from the very basic. So I'm using von Neumann architecture, which is also called Princeton architecture. It was proposed in 1940s, and a lot of modern compute are still based on this model. This is very early understanding, but essentially it just goes on to say that to process information, there are this conceptual boundaries. So there is always an input device. So let's take example of large language model again. So this will be a plethora of data, just the unstructured data. So that will be input device. So this could be SSD in our case when we are talking about large language model. So that information has to go through a central processing unit. So when von Neumann made this architecture, he was not talking about accelerators or GPUs. He just meant any control or arithmetic logic unit. So in our case, in modern example, we can consider this as a GPU. And there is a memory element. So the bottleneck here is there is only one connection here from compute unit to the memory unit. And based on its limitation, the kind of processing or the throughput you deliver will be limited. So to increase throughput, the options are you can increase number of central processing unit, and then you can increase memory, and you have to also have to increase the bandwidth between these two. So let's look at how industry evolved. So it shows the processing in the green color here, compute, and memory availability in the red color. So for the early 10 years of this century, both compute facility and memory facility increased in tandem. So people were adding multiple cores in the CPU units, and the memory availability was also increasing through next generations of DDR DRAMs. But what started happening around 2010, 2012 is we were able to add a lot of compute. So we started seeing a lot of processors in the hyperscale data center market where you have 40 core, 60 core, 96 core, 138 core, about 196 cores. But memory availability got limited because the bandwidth here is limited. The bandwidth did not go as fast as possible, and the memory cannot be shared by different compute. So although we made a lot of progress in adding number of core in a compute facility, but we couldn't provide the memory so that these kinds of compute problems can be solved. And this became the gap. And there are a lot of public publication, Meta, Microsoft, and Google, all of these have publicly talked about this memory wall. They have not used the same word, but that's the problem they have been highlighting. And the way industry is trying to address this problem is to by providing a CXL interconnect, Compute Express Link. So CXL utilizes the same PCIe physical layer. So I'll talk about the physical layer or the division of this layer. But at this point, the message here is CXL builds on already existing PCIe infrastructure. And in addition, it solves this memory wall problem. So what CXL does as a protocol is it extends memory semantics. So memory semantic is how you can address all levels of memory contiguously, meaning if you add more memories together, can your program or software address them contiguously, or there are some gaps or it has to make some hop. If there are hops to be made, the memory is not contiguous and your throughput gets limited because of the memory wall. So this is the same point I was making earlier. CPU core count increased by 3x, but memory bandwidth per core actually have reduced. So we need to solve this problem. And this is what CXL does, that a memory is not tied down to one processing unit. So this is just using a generic word X processing unit. It could be data processing unit or graphical processing unit or accelerator. So the idea here is what CXL does is through its protocol implementation, the memory available for this GPU can be shared by this memory, this DRAM memory. And the reason I'm showing this in different implementation, that now you can mix and match. You don't need to have one kind of memory. So here I'm showing a DDR dual data rate kind of memory, which goes on a socket through a DIMM package, dual inline memory module. But this GPU can have an HBM memory, high bandwidth memory, which is a die-to-die kind of interconnect memory. So all those DRAM memories can be shared with each other using this CXL. So now memory is not tied down to one processing unit. So this solves the problem of memory limitation. And that's very useful because to process this large language model, let's say the CPU was solving a relatively smaller problem and it had some DRAM which was available but not utilized. But whereas this DPU was doing some token based work where it needs a lot of memory, but now because memory is not tied to one of the processing unit, this DPU can access the memory of the CPU at about the same latency as its own cache. And that's the advantage of CXL, that all these distributed compute facilities can process that workload together at very low latency. So the latencies we are talking about here ranges from 40 nanosecond to 120 nanosecond, which is about L3 cache. So this CXL offers this very efficient way to extend the memory semantic and address the memory wall problem. So those were at very high level of what we're talking about, next generation interconnects and the problem we are solving. Now let's look into present day deployment. So this information is publicly available at top 500. So I've just taken screenshots from there and it shows what's deployed today. And it focused on high performance compute cluster. So it's not generic data center. Is, for example, the number one compute facility here is the Exaflop Frontier in National Oak Ridge Laboratory. So we are talking about those kind of compute clusters, and you'll find a lot of hyperscale data center compute clusters there as well. Amazon, Microsoft, Google, all the compute clusters are listed there. So this at very high level talks about different kind of interconnect. So first information was very easy to get from there. So this is about the packet-based interconnects. So here it looks like Ethernet has a slight more deployment compared to InfiniBand. So 45% of total deployments in today's top 5 high performance compute cluster are connected through Ethernet. So it says gigabit Ethernet, but when you double click into this, you will find that it's actually 100 gigabit interfaces, and InfiniBand is also 100 gigabit. So GBE actually means gigabit Ethernet. And in this presentation going forward, I will use 100 gig, 200 gig, or 800 gig to make a generic reference to both of these packaging technologies, which are Ethernet and InfiniBand. So here I wanted to make this distinction. That's why I have said gigabit Ethernet instead of 100 gig. But going forward, I'll just say 100 gig interfaces, and I'll mean these technologies. And then on top of that, there are different specific implementation. So there is this Omni Path Interconnect, which is from Intel. And then there are other enhanced IO custom proprietary network. So at very high level, this is one set of technology, interconnect technology. And second, to get a PCIe or CXL kind of deployment, it was a bit difficult. It's to get this information from top 500. So I went through a roundabout way. I found the different processors that are used, and through their website, I found which PCIe or CXL technologies they deploy. So for example, Skylake, you can go and find out deploys PCIe Gen 4. So majority of the deployment today is PCIe Gen 4. So when we get amazed by ChatGPT output, we should keep this in mind. The interconnect today are just PCIe Gen 4 and 100 gigabit Ethernet or InfiniBand. So when we talk about next generation technologies, we can see what output or throughput or what power generation it can lead to. Now, this is a slide where I'm comparing two different protocols or interconnect technology from the protocol point of view. And I, again, wanted to start from our 101 reference, which is a networking 101 from the open system interconnect reference architecture, which we learned in our college, which is an abstraction layer, which just separates different tasks of networking. Then when you have to go from one chip to another, what are different tasks that you need to do? And these two protocols, both Ethernet or InfiniBand or PCI or CXL, actually address just the physical layer and data link layer. So Ethernet is L1 and L2 protocol. Anything related with networking has to be done on top of Ethernet. And this is mostly done in the digital domain. But our focus of interconnect is mostly on the physical. But in this slide, I'll just touch upon the other point just to make this bigger case that it's both hardware and software problem, not just the software or not just the hardware problem. So main focus will be on the hardware, on the interconnect. But in this slide, let's just look into what else goes into a networking protocol. So as we all know, Ethernet is L2 or L1 protocol, just called L1, layer 1, layer 2. So Ethernet just defines up to L2. So that's the protocol. And then on top of that, you have different TCP IP protocol that completes this stack and completes the total workload. And IEEE defines the Ethernet. And this is the division they talk about. If you go to IEEE spec for different generation, they define the task of the physical layer. So as you can see here, there are different logical abstraction or different type of interconnects that the standard define based on the medium. So here, this is one implementation of 100 gig based KR1 modem. So KR is, so there's a different nomenclature and I have referenced it. You can find out what each of these later meant. And what it means is 100 gig throughput or data rate is achieved through one lane. So the link, which is aggregation of multiple lanes, will have the same throughput as one lane. So you have only one lane which has 100 gig or 100 Gbps of throughput. And on top of that, there are different logical layers which serve their own purpose. So AN shows auto negotiation because this link will interface with another chip, and this link has to find out the highest data rate these two chips can talk together. So the process is done through auto negotiation. So the first link will establish at some data rate, and both the chip partners will figure out the highest data rate, and that's the rate this link will start operating. And then there's a physical medium dependent. So as Ethernet runs over optics, backplane, which is PCB, direct attached copper, active electrical cable, and so on and so forth, based on the physical medium, there are some functionality that needs to be implemented, and that is defined using this PMT. And then there is a physical media attach, which is called PMA. So this layer talks about how this physical media dependent functions attach to the other media. So this again, based on electrical and optical deployment, there are different digital functions that the standards talk about. And then there's finally forward error correction. All this high-speed interconnect technology run on this digital error correction technology, which is called forward error correction. So based on the packet we are transmitting here or the information we are transmitting here, we add some, to use the loosely common word, parity bits. So parity bits are generally used for cyclic redundancy check, but I'm using the same concept to make a case for forward error correction. So this is again a digital function that is suggested by the protocol. Most common are Reed-Solomon 514 to 544 FEC, forward error correction, which would mean that you will take 514 symbols or bits of that information and pad it to 544 so that you digitally correct the errors which will be estimated by the channel. So that again is defined by this protocol. And then there is this layer which called physical coding sublayer or PCS layer. So this also has some functioning like scrambling and error padding like 64 to 65 bit or 64 to 66 bits. So those are again protocol specific based on where it's being deployed. So all these are defined as the physical layer functions by IEEE. And when we talk about one protocol, we are talking about all these digital layers that we define. And then on top of that, you have a MAC layer, media access control. And then on top of that, you have a higher software layer. So this goes on to Ethernet or InfiniBand kind of switching protocol. And here, again, it's a different example where 200 gig throughput is implemented using 2 lanes on the backplane channel. So K means backplane, R is 64 to 66 bit encoding, and 200 is the total throughput. And this goes on to show 400 gig total throughput using 4 lanes of 100 gig SerDes over a backplane channel using 6466. So those are different layers. So this is data link layer, which is defined by Ethernet. And very quickly to compare it with PCIe, it's not a one-to-one comparison because PCIe or CXL are not networking protocols. They are for end-to-end link. So there's no equal uh, representation of all this layer between Ethernet to PCIe. But just to make this point, physical layer and data link layer can be mapped into the phi function. So physical layer is phi in short. So in PCIe CXL, you have a phi. And there's also data link layer that this protocols define. So if you go through a PCIe SIG specification, you will find the transaction layer work, which is roughly equivalent to what IEEE does for Ethernet. And then they also have PCS equivalent, physical coding sublayer, which also does the scrambling function as Ethernet does. And PCIe Gen 6, which uses 64 gig PAM4 signaling, also has a forward error correction. So now both of these stack look very similar, but the difference at high level are PCIe CXL are end-to-end, which can be used as memory mapped IO. So you can do cache coherency over PCIe CXL. But with Ethernet, the latencies will be higher. There are technologies like Rocky, RDME over Converge Ethernet, which also provides this kind of end-to-end memory coherency, but the latency in those implementation are significantly higher compared to PCI and CXL. So with CXL, we are talking about 25 nanosecond of latency, but with Rocky, this will go about 200 or 250 nanosecond. So that's how interconnects from these two protocols are selected based on where we have to implement. And this was the point I was trying to make, that if we were to solve this problem, this aggregated architecture, where we have to process large language models, we need to use CXL kind of interfaces so that the memory can be used. But if you use memory can be used coherently. But if you use Ethernet, the latency will be so high that the processing will actually miss the tokens and you would not be able to process the sample. So those are the two problems we are trying to solve and the different interconnects we are talking about. So now let's look deeper into the electrical interconnects for Ethernet and InfiniBand. So now instead of using these protocols, which refer to different layers here, DLL, I'm going to focus only on the physical layer, and which I'll use interconnect as a word, or electrical interface for this kind of packaging technology. So here I'm just using 112 Gbps data rate. And I also want to take a moment to explain why there are different numbers that float around with one data rate. For example, in Ethernet world, you will find 100 Gbps word. For example, there's a standard is called 100G base KR. But if you look at the throughput, which will go in the SerDes output, or let's say I'll go here, so this shows the stack, and the throughput you will have the real. So this is a medium. This will be PCB or it will be copper cable. So here, if you are running 100 gig Ethernet, the data rate here will be 106.25. And the reason for that is the overheads all of these layers have. I roughly talked about scrambling and I roughly talked about the FEC, and that would have given you an estimation that both of those processes add additional padding or additional bits. So if we were to transmit 100 Gbps data here, we need to pad that data. And based on this protocol layer, the real SerDes data rate will go higher. So based on Ethernet 100 gig, if you were to pass packets at 100 gig, the SerDes have to have throughput of 106.25 Gbps. So as a SerDes designer or electrical interconnect power, what is of our interest is 106.25. So this is Ethernet, but OIF tries to define the electrical standard, which has wide adoption, not just for passing Ethernet packets. OIF standards are also used for InfiniBand, fiber channel, and they focus only on electrical. So they need to define an electrical standard that accounts for all those overheads that other protocols might have. So that's why OIF generally takes a 12% overhead. So if we were to pass 100 Gbps packets in Ethernet, Ethernet will only talk about, IEEE will only talk about 106, but OIF takes a wider approach and defines for 112 Gbps so that other protocol stacks, maybe fiber channel, might need a different overhead, and those are addressed too. So those are just the data rate. Now look at different channels. And one metric that is used to define the channel is the loss as the Nyquist frequency. So Nyquist frequency is the bandwidth where the frequency component of the signal resides. And if we pass that bandwidth, we can sufficiently transfer the data at corresponding bit rate. So based on the modulation, the Nyquist is decided, and the loss at that Nyquist decides the power that the interconnect has to burn. So both these electrical interconnect standards try to define different channel losses, and they vary from 2 dB to 35 dB. So let's take example from IEEE. So IEEE, if we were to, let's say, pass Ethernet packets from one chip, and what I show here is a AUI interface. So AUI is attachment unit interface. There's a AUI layer here as well. So what IEEE does is it defines a channel. So from one chip, you will have a connector, and on the other side, you can have another chip or a module. So this is the channel loss we are talking about. And this roughly translates into a VSR, or very short reach equivalent loss by OIF. So you would see that OIF VSR also address the seminal channel, that chip to module. So there's a connector. So I can probably show it in the first diagram. So what it's defining is from the chip, or let's say the switch, instead of this retimer, this optical module goes through a connector. So that's the channel we are talking as VSR. So that is defined with a channel loss like 16 dB. And this is the Nyquist frequency. And PAM4 is the modulation scheme. So they're based on different reaches. IEEE and OIF have defined different interconnects, and they have different power profile. And based on how they are deployed, the total power consumption gets either higher or lower. So I'll talk about this a bit in detail, but this just goes on to show there are different channels we are talking about, and the loss number at those channels are the key contributor for the power dissipation. So at very high level, so there is chip to module, and chip to chip with two connectors in between. And there is a 2-meter twin axial copper cable. So now we have started talking about 30 dB of loss. And then this is the KR, the backplane I talked about. So CR is through copper cable and KR is on backplane. And the loss target are about equal for these two. And for 100 gig, it's like 28 dB without the package loss. So those are the losses IEEE have talked about. And when OIF started talking about this interconnect losses, they started this 112 gig work in 2018. So it's been 5 years OIF has working on this. And when they started, these were the 4 reaches they imagined or they planned for. But as the deployment progressed, they were other interconnect reaches which were of interest. So I'll talk about how they panned out, but let's go back 5 years and look into the different reaches uh, of 100 gig electrical interface that standard body or the hyperscalers were talking about. This is the XSR interface, extra short reach. So this we will talk in detail when we go to die to die. And it just goes on to show that there's a 2.5D chip. So within a chip, you have one die, another die, and these are connected using something called interposer. So the loss here is about 10 dB, which is really low. And this is a serializer, deserializer based interface that OIF has talked about. So these were the four standards which it started. And if you look at how these are deployed, or when somebody has to implement this in real chip or a semiconductor processing unit, what are the blocks we are talking about? So at very high level, the reason I'm trying to make this point is as the channel reach increases, you need more blocks in the SerDes, serializer or deserializer, to process that, and each block takes power. So when we are talking about the whole interconnect power, we need to just see how many blocks you need in that serializer, deserializer. So I'm taking this example of OIF that they started 5 years back. And to address this, for die to die, so this shows a host PCB. Now this is the side view of a rack unit. So if you look at the rack unit from the side, you will find a host PCB. On top of that, there will be package substrate, and there are multiple dies. So these are not chip. Chip is something that goes and sits on a PCB. That's the traditional definition of chip. But inside the chip, you have a substrate. So this is what I show here. So if you break open the chip, you will find a substrate. And on top of substrate, you have multiple dies. So this is the die which is manufactured by a foundry, and it goes to a bumping house or a packaging house, and you get all these bumps, and you connect multiple dies together on top of this substrate. So this implementation shows you have a switch die which will do the switch function that I was showing earlier. And then it will have a SerDes, serializer, deserializer, which is designed for extra short reach. And the channel the SerDes will see, meaning the transmitter of the SerDes, needs to transfer through this package substrate and drive another XSR here. And then there'll be a digital signal processing, and it will drive an optics. So it shows an implementation of a switch, which is implemented as a single chip using multiple dies. And to drive this, you need a SerDes, which is XSR, and we are talking about 10 dB of loss. So if you were to implement this, I'm showing receiver here, as receiver is more complicated block in a SerDes, in serializer, deserializer. So in the receiver here, you don't need a full-fledged clock and data recovery. So here, because it has to compensate only for 10 dB of power, it's relatively lightweight receiver. So from the receive point of view, let's say in this XSR receiver, it goes through a T coil and resistor termination. So this is the way the receiver signals are terminated. They look like T coil. That's why I call T coil and resistor termination. And there is a DLL, digital delay lock loop, which is sometimes implemented in digital domain and also in analog. It does phase align, and then through sampler, it deserializes. So because it has to compensate for 10 dB, which is not such a big loss. So this is simpler receiver, and the power efficiencies we are talking about here are 1 to 1.5 picojoule per bit in modern CMOS technologies. So this is one kind of interconnect that has seen a lot of deployment. Then second interconnects, what we see is VSR-based interconnect, very short reach, and they typically go from switch to retimer. This is again what I showed in early slide, and then drives a module. So here I'm showing a bit more granular depiction of module, where this is the pluggable module. So this would be a cage. And here you have this module that plugs in, and there's an optical engine. We'll talk more about this in coming slide. But the idea here is to talk about different channels. So this retimer has to drive this bump, and now it's going through a PCB. And now that it's PCB, it has to go through this connector. So this connector will have some discontinuity, that will be a larger loss, and it will degrade the signal more. And then it will go through an optical engine, and then there will be optics from here. Second implementation could be without retimer, where the ASIC will directly drive without a retimer through an optical engine. So this ASIC will be, let's say, CMOS 3 nanometer, 5 nanometer technology, and that transmitter has to drive the bump, which will go through substrate and will go through package, will go through this PCB, then through this connector, which is a cage, so there'll be reflection, then another bump, then optical engine. So here, as you might imagine, the loss have increased. And for the VSR, we are talking about 16 dB of loss at the Nyquist frequency of 112 Gbps. And here we need slightly, not slightly, significantly more complicated receiver. So as you can see here, there is a variable gain amplifier, there is a CTLE, continuous time linear equalizer, because now the channel has become more complicated. There are reflections, there is something called ILD, insertion loss deviation. So all those needs to be corrected in the receiver. And to correct all those non-idealities, you need all these different blocks, and altogether they burn power. So this shows one example. And VSR SerDes can be implemented both in analog and also digital domain. So there's way of implementing it just in analog processing, and you can choose to implement using analog to digital converter and through DSP. And this shows clock and data recovery. So this shows a full-fledged CDR loop, whereas here we were able to do with DLL. So this takes more power. And here we are talking about 2.5 to 3.5 picojoule per bit of power efficiency. And now this becomes the most complex channel, which is shown here with two connectors over a backplane. So you could have a riser card and one, let's say, SerDes here, which will drive the channel, which will go through this connector, through another PCB, will go through another connector, through the PCB, and to the other die package and everything. So here we are talking about 28 dB of loss. And to equalize this kind of channel, you do need an ADC or DSP based kind of receiver architecture. And as all of these blocks take power, we are talking about 5 to 6 picojoule per bit of power just to transmit one bit from here to another chip, which is on the another PCB. So to save power in all this interconnect, area optimized, low latency, and low power implementation of this SerDes technology is a holy grail. So now fast forward to today, after 5 years of working on the standard, OIF ended up defining 7 standards for 112 gig electrical reaches. And you would notice, so this is from their website, thanks and all courtesy to them. You would notice there are 2 new standards or the channel they have talked about. And also there is this multi-chip module. So let's look into all this. And it's very good reference as they have talked about all the key parameters which are used in this interconnect, and they have provided a guidance to the industry on type of power efficiencies they should target about. So when we go from top to bottom, the loss increase, so the power taken to compensate this channel will also increase, and power efficiency will go down. So that's how this correlation works. So starting from very top, again, we'll talk about this 2 standard when we go to die to die. These 2 are die to die standards. First is multi-chip module. And here you will see a 3D stack of different dies. So this die can connect to the top die through something called through silicon via, and the signal has to go from this die through this interposer to the other die. So that's the channel we are talking about. So it's minimal channel, but there are reflections here. And then it's called 2.5D because you're not passing through anything. When you pass through something, it's called 3D. So this is 2.5D implementation. It's chip to chiplet. So here the modulation scheme standard is talking about, it's called CNRZ. It's chord signaling. And very few implementers, to be very frank, have selected this implementation for die to die. But this is a standard which is up for grab. I'm not making personal choice or any comment here. It's just the fact. And the second is this XSR, extra short reach. Here, we talked about this earlier. So what we are talking at 10 dB loss at 28 gigahertz Nyquist, because we are using PAM4 modulation here. So Nyquist will be 1/4 of the data rate. So 1/4 of 112 Gbps is 28 gig. So that's the loss we are interested in. And it can cover up to 50 millimeter of packet substrate. So these two standards are only for within chip or within package. Now, this is something new, and we will talk about this. So this is the linear interface where the chip to pluggable optics interface. So this is what we've seen earlier a couple of times, where the signal starts from a chip or switch, goes through a connector, pluggable cage, or goes through pluggable optics. And here, the idea is instead of having a retimed interface, the chip will directly drive the optics. So here we are talking about 11 dB of loss. And the important point here is this doesn't need DSP or SerDes in optical module. We'll talk about this, but the point I'm trying to make is this is a new standard that OIF started talking about. And the reason for this is offers better power efficiency. Then this is something new, XSR Plus, which enables the NPO or near package optics. Here you would see through one connector, optics is connected, and the loss has gone up from 11 dB to 13 dB. And there is a power efficiency target here, 1.8 picojoule per bit. So now the standard itself talk about the total power efficiency, and it's a really good step to save total powers through interconnect. Now, this is the VSR, MR, and LR we talked about in our previous slide. And finally, there are some additional standard which are not defined by OEF, but implementers are asking for, and different companies have different names for it. So the request from industry or the type of deployments the real data center sees are more. So although the channel reach here was 28 dB, there are a lot of implementation which goes up to 40 or 45 dB and takes more power. So this just shows the complication of the deployment in new generation of interfaces. And now I'm sharing a couple of slides, what will happen to the next generation and generation after next. So till now, we talked about 100 gig. And as you would notice, I'm not giving reference to Ethernet or InfiniBand. It's just 112 gig a generic term. And now just one slide to summarize where we are with respect to the next generation or 224 gig. So here I'm just trying to show the journey of a packet from an accelerator to another accelerator in a different form and the different interconnects that go in between. And I just wanted to make some comment on where they are today. So within a rack unit, CPU to GPU, as we talked, that CXL solves the newer problem. And CXL 3.0, which uses the same physical layer as PCIe Gen 6 at 64 gigatransfer per second PAM4, is ready now. So there are people who are designing those chips. So that exists. And the mapping you have from NIC to Ethernet, typically a 16 lane of this memory mapped IO translates into the total throughput here. So let's say PCIe Gen 6 is 64 gigatransfer into 16 is about 800 Gbps Ethernet equivalent or 800 Gbps InfiniBand equivalent. So those kind of modules have started being designing today, and they can drive direct attach copper. And the key thing here is the active optical cable or the optics side of it. So what people were initially concerned about, whether this 200 gig data rate can be supported with PAM4 modulation or it has to go with PAM6. But the good thing there is PAM4 200 gig lambda has started seeing production ramp. So this piece of puzzle is also ready today. And as we see the deployment from the industry, every 2 years, the total throughput of the switch has increased uh, predictably from 2016. So 2022, we have seen 50 terabit switch. So the industry expects that by next year end, there will be 224 gig switch by 2024. So that part of puzzle is also solved. And module, there have already been talks about early shipment of 224 gig. So it looks like people can see the whole ecosystem with 224 gig started being shaping up from the next year. And the way these interconnects have been designed and the way their power efficiency is targeted will define the total power in the next generations. And this is just one slide before we break for question answer, is what after 224? And so this is already the next generation we are talking about. And this is just one slide. And from electrical interconnect point of view, what are the key things from data center perspective? We have to take power efficiency of each of these interconnect in account. Like optics, if we are burning significant power in optics, and if the electrical throughput is not matched with optical throughput, we need gearboxes in between. And those gearboxes will have to drive electrical channel, and they will also take power. So which way to go for the next generation in 2026 or 2027? So this is just the electrical SerDes designer point of view. And this shows the baud rate or the Nyquist frequency I was talking earlier about. And this shows the data rate. Based on the different modulation scheme, baud rate changes. And if the baud rate goes higher, you need more blocks in the receiver and transmitter to compensate for the losses. So if we keep the baud rate same and just increase the modulation scheme, so what we are saying is power should not increase as much, right? So that's very high level idea. So that's one of the reasons NRZ was replaced by PAM4, that for the same baud rate, you get 224 gig throughput. So if we had NRZ modulation for 2 to 4 gig, the throughput will get only 112 Gbps. So if we need to keep the same baud rate and just increase the modulation type, let's say from PAM4, we go to PAM6. So we can still go to around 350 Gbps. And if we go to PAM8, it could be higher. And then there's coherent modulation, which is quadrature amplitude modulation 16, COM16. For the same baud rate, you can go up to 448 Gbps. So that's very narrow SerDes power dissipation perspective as well. But when we talk about the whole ecosystem in the data center, there are other things that we need to take into account as well, like the need of unified modulation scheme for electrical and optical link. So this is what I was alluding earlier, that if the modulation schemes are different, you need gearboxes in between. If one side is NRZ, other side is PAM4, you need that gearbox, and that itself will take a lot of power. And historically, the optical modulation for the given link decides the corresponding electrical SerDes. So it's actually up to the next generation optics designer if we get a 400 gig lambda. So 400 gig lambda means one single fiber can carry 400 Gbps of optical information. And if that modulation takes PAM4, then the electrical SerDes designer will have to design 400 gig PAM4 because we want to save power in that gearboxes. And this is just the comment that the higher baud rate increases electrical channel loss as it needs more length, and the shorter links will save power. So this was the point, very focused SerDes point, but the first 2 points try to make a overall data center point. So all these three needs to align for the next generation. So these are at very high level, the options we have. And I think I have this couple of slides on optical, but I think we are about an hour time. So let's take a pause for the questions if we have any.
Sounds good. Thank you very much, Priyank. This is great. I don't see any questions in the Slack channel, but yeah, please feel free to type them there if you have any. Let me just ask a few. First of all, thank you very much for this tutorial. It is, I think, fantastic, especially for a guy like myself that, doesn't have a strong understanding of all these standards and the differences and all the acronyms. And I thank you very much for example, for defining every single acronym. I think I've learned quite a bit already. I was wondering maybe if you could just describe what's your involvement with the standards bodies. It sounds like you're a voting member for IEEE. And is that true for OIF as well? And what's it like? And
That's correct. So
what's your role?
IEEE,
Yeah.
I'm the voting member. So the way it works in IEEE is they have quarterly meetings and you have to attend a significant number. So in 1 year, you have to attend two, and you have to attend number of sessions, then you have to contribute to the standards which are under development. Then if you continue doing that for a year and a half, then you get the voting rights. So you have to earn your membership to contribute. And you can pick and choose different work groups you want to take part in. And I take part in this 200 gig electrical work group, and have been involved in 100 gig electrical work group as well.
Nice. And it's is it an enjoyable process? And
It
do you find
is.
it's
Yeah, I
the
mean,
progress is steady?
yeah, so what I
Sounds
really
like it.
like is, right, the more things change, the more they remain the same. So in 2011 or 2012, if you start seeing when we were migrating from 10 gig to 25 gig, people were starting about this PAM4 and PAM6, all that. They're
Yeah.
talking about different FEC. The same thing happened for 100 gig, same thing is happening for 224 gig. So we always surprise ourselves. We always underestimate how good progress we can make over time. So that's a great learning. And also seeing your name in the standard, when the standard gets published, all the voting members see their name. So I'm very
Yeah.
happy to find my name.
Yeah. That's great. Um, so I'm not seeing any other questions.
Shall we take 5 minutes bio break and
I
then
think
we'll
so.
resume?
Yeah. Sounds great.
Okay, let's
All
take
right.
a
So
pause for
let's
five
take
minutes.
5
Thank you.
minutes and we'll see you right back here.
So is it all right to start?
It is. We do have one interesting question. If you don't mind fielding it now.
Absolutely. Let's look at
Yeah,
that.
it says it's actually in the Zoom chat. Since the link layer in UCIe is not defined, how can interoperability with UCIe from different vendors be ensured?
Absolutely. I'll address that question when we talk about UCIe.
Yeah, yeah.
I can show that slide
Good
and
timing.
I'll come
Yeah,
back there. Yeah.
sure.
So this is that slide about a UCIe protocol stack, and I'll address when we come there. So it's 12 slides away. So I think I'll take 40 minutes to reach there. Okay.
Sounds good.
Okay. So maybe I should pick up speed a bit and start from here. I'll turn off my video, get to it. Okay. So this is where we stopped. So we talked about this electrical interfaces and how it all has to work together. We have to look at whole power. Now let's look into electro-optical interface in detail in the boundary of electrical to optical conversion. So let's start with what's deployed today and what's happening in the data center. Again, I'm using 400 gig, 800 gig, not picking between Ethernet, fiber channel, or InfiniBand or anything. So this shows based on the reach or the channel length for the optics, different types of modulation scheme and different types of fiber that are used. So all the previous comment I made was for electrical SerDes. And I made very simple sweeping comment that the more the channel loss, more the Nyquist, more the bandwidth, more the power would be. But in optics, that's not how it scales. So let's look into that. So the 2 points I'm going to make here are for 400 gig Ethernet. I'm picking Ethernet here and 800 gig Ethernet here, just to make overhead similar from the electrical data rate to the protocol rate. So for 400 gig, what we are seeing is inside the data center, start from, we have seen even 30-meter, 10-meter optical deployment. From about 40 kilometer, we have intensity modulation, direct detect or IMDD modulation, which is just a PAM4 from electrical point of view. So for these kind of reaches, it's a PAM4 in electrical, PAM4 in optical. So you don't need to burn in this gearboxing and there's no additional DSP needed. And for different reaches, you have different kinds of fiber that goes to have this kind of optics being driven. So for short reach, which is about 100 meters for optical, you have multi-mode fiber. So these are the cheapest implementation where you have couple of modes of optics in the single fiber. And then if you have to drive higher lengths, let's say 500 meters within the data center, so you have PSM or parallel single mode fiber. So this fiber becomes more expensive, and the standard from IEEE we are talking about is the DR. And then if you are going for FR, so this is about 2 kilometer kind of range. So here duplex single mode fibers are used, and single mode fibers are more expensive as they cover higher lengths, and you need a different kind of DSP or digital signal processing to drive this optics. So I'll cover what is needed to design that DSP in the next slide, but at very high level, based on the distance, you need to burn power in doing the equalization for optics and electrical domain. So that we need to keep into the mind. Finally, with 400 gig, we started seeing coherent modulation, which is QAM 16, QAM 64, QAM 32, quadrature amplitude modulation in data center. So coherent has traditionally been used for very long haul, ultra long distances, thousands of kilometers. And the reason for that was the DSP or the digital signal processing that we need to do to drive the optics for such long distance took a lot of power. And you can't have a pluggable module with that kind of power dissipation. But with the progress of CMOS technology, now it's possible to make a pluggable module. So this is a module. I'll go back to my slide that shows the picture on where it plugs in. So now we are talking about this faceplate, a very small form factor, which is called QSFP-DD or OSFP, which is pluggable on this rack unit, and that will have a DSP engine that can do this QAM or coherent modulation digital signal processing and drive up to 120 kilometer of length. So that's the modulation, and it's called ZR. So OIF has defined the ZR. IEEE did not define the ZR, but there are different limitations here. And the way it's going to move is when 800 gig deployment sees coherent modulation, will start seeing deployment with about 10-kilometer links. So it's called coherent light. And the logic here again is the CMOS technologies have progressed so much that it's possible to do digital signal processing needed for coherent modulation in the same power envelope. So this itself is saving a lot of power, which is burned in electrical to optical interconnects. Because if you consider with 400 gig, you would need two hops with LR SMF, but now with one hop, you are implementing this electro-optical link in a power efficient way. So industry is moving towards this power efficiency improvement, and this is majorly driven by innovations in the DSP technologies. So these are very smart and innovative designers who are implementing these algorithms in advanced CMOS process node and making sure that this modulation schemes are possible in this data rates. Now let's look into present day optical module. I showed previously where it fits into. And if you break open the optical module, these are the different dies you will see. So here I'm using the word die. You can use word chip as well because they are going into one package, one PCB. So this is one PCB, and on that PCB you have multiple chips, but it's not very uncommon to see one substrate where there are different dies. So there are different kinds of integration. With silicon photonics, it has become possible that in one substrate or one package, you can integrate all these modules together. So there are different companies who are pioneering this technology, and the holy grail in that silicon photonics is to integrate the laser. So let's talk about different blocks in the optical domain. We touched upon the blocks which are needed in electrical domain, which were the CDR module, where VGA and CDLE and so on. On the optical side, I'm showing those in different color here, different versions of blue color here. So on the transmitter side, so this is the transmitter side of the optics, you need a driver, you need a laser, and you need a modulator. So that converts the electrical signal to the optical signal. So laser and modulator together creates the light that will go to the fiber. So output of this side will be the fiber, the transmit side of fiber. On the receive side, that goes through a photodiode, and this converts this light information to electrical domain, and it goes through a trans impedance amplifier, and there it goes to an electrical domain. So this true this true dark blue color can be implemented in a electrical CMOS process as well, advanced process node. But this light blue color are optical processes, and they are different processes, different foundries, and those are de designed by some boutique foundries. I don't want to take public names, but so these come from an optical manufacturing facility, these three light blue, and their implementation where this dark blue are implemented in advanced process nodes in CMOS manufacturing unit, and sometimes they're combined with the physical layer, the electrical interconnect we are talking about, and the DSP here. So this DSP is the digital signal processing that is needed to drive this modulator. So this light blue color, let's say there is a monolithic implementation in this photonic process node, which integrates these three together. And what it needs is just driving from electrical domain. So one possible implementation could be this 5-block driver TIA can be implemented in advanced CMOS process node, and that just drives this optical die. So in that case, you will see implementation, one electrical die and one optical die. And this side goes through the switch. So we talked about this implementation, the VSR5, with or without retimer goes through the switch. So from that signal, there is a DSP. So there are so many interconnects here. So that's the present day implementation. And just for the sake of completeness, there are some microcontroller unit that configures the module in different modes, because this could run at 100 gig lambda, 50 gig lambda, 25 gig lambda. So all that's controlled there. Driver is the linear amplifier. Laser. So just want to make this comment. There are some advanced technology where this laser as well can be implemented in a single silicon photonic die. So people are talking about quantum dot technology. So this could be a monolithic implementation. So there are vendors who, when you open their optical module, you just see two dies in a package, and that currently operates up to 100 gig lambda. So a lot of power has been saved. A lot of power has been saved by doing the monolithic integration, because the more integration you do, you reduce the need of electrical interconnects there. So if you have these two in one die and this is another die, you need to drive a die to die interface. And now you're burning 1.8 picojoule per bit, as I mentioned, which will be like 100 megawatts if it goes to total deployment. So that's the progress we are seeing. And this was the point I was trying to make when I was talking about different dies. So in silicon photonics implementation, it's possible that laser modulator, driver TIA are in one silicon die, and all these are in different die advanced CMOS process node. This could be in 5 nanometer, 3 nanometer to save more power, and these are integrated in this optical module. So this shows multiple dies or multiple chips, and this shows some advanced deployment of optical module where you just have two dies together. So that's how we are saving power. And now let's talk about the new standard I was alluding to earlier. So this is the linear standard. Let me just go back there to make this point. So this is the linear. Now we are double clicking on what this entails. So this proposes to replace VSR. So in VSR, as we saw from the chip or the switch, you have connector and there's a VSR PHY, and we looked into what goes into this interface. So this is the implementation. So here there would be a switch, this channel, then VSR PHY that will burn power, then DSP and this module. What this new interface suggests, so I have better picture here. So this shows the full picture. We are talking about so many electrical interface. So this would be switch, which will have traditionally a long reach PHY, which will operate for 15 dB kind of loss. And then this is the module where you have VSR PHY, DSP, and here I'm showing the driver and TIA are implemented in advanced CMOS process node so that it saves more power. And this is a photonic die. So this is the present implementation. This is called conventional, or it's called retimed interface, because we are doing a retiming using a full-fledged PHY here. So there's a clock and data recovery. And if you recall, that's a block that takes a lot of power. So this takes more power. So the argument here is there is one electrical interconnect that burns power, another electrical interconnect, then you do DSP, and then there's another optical interconnect. With the process node advancement in the CMOS technology, the argument is this DSP functionality can be pushed to this LR. So this LR PHY, long reach PHY, already has a lot of digital signal processing. And the argument is the modern optical dies are so efficient that this DSP can be just implemented in the LR PHY. So this is the proposed low power. It's called direct drive. It's called non-retimed. It's called linear. It's called analog drive. What it means essentially is in the optical module, you are not retiming the signal. Like here, you are doing clock and data recovery, but here you're not doing that. And the DSP function is subsumed in the long reach PHY. So long reach PHY, if you recall, has so much DSP in the receiver that it can compensate for 35 dB of loss. So the argument is, if I reduce the loss between these two channels to, let's say, 15 dB, the LR PHY still has horsepower to compensate for this optical non-ideality and non-linearity. And by doing this, we save power in this retimed interface. So there are a lot of challenges here, but the standard bodies are working towards making this possible. There are different interconnect points proposed and being considered together today. So at very high level, what this does not allow is interoperability. So it becomes sort of a closed ecosystem that these two blocks need to work together, and that's how it will work. But it's not so much interoperable. And the other market dynamics here is the pluggable module vendors have to make sure that it works with all switch vendors. So that's the market dynamics. But from power point of view, it definitely saves power by at the cost of interoperability. And the standard body is working to make sure that we save power and we ensure interoperability. So that's a new trend we are seeing to save power. And the interoperability part, the way it's proposed today, is by this. I'm showing here electro-optical electrical link. So this shows the complete link that I've been trying to show, that a transmitter transmit goes through an interconnect loss or a board, and it then drives the optical component, let's say laser, and it goes through a fiber, then goes through a photodetector, the trans impedance amplifier, then the interconnect loss, it could be PCB, and then it will go to receiver ASIC. So that's the full path we are talking about. And we need to ensure that this electro-optical electro interoperability is ensured. So there are different ways of ensuring this. People are talking about an IBIS AMI based model where electrical channels, the electrical vendor will provide their transmitter model, receiver model, interconnect losses, and optical vendors will provide the IBIS equivalent model for the whole link. So people or implementers can make a test bench which will have this whole link and they can simulate together. Also, there are uh, photonics tools that are available today where you can do this complete link simulation. And here I've just jotted down different parameters which are of importance here and how complicated it is to ensure interoperability here, meaning the performance of this link depends on the interconnect loss here. There's a package involved, package loss, board loss, the discontinuities I was talking about. Then the laser driver is not always ideal. The gain, which varies with frequency, distortion, noise, those needs to be taken into account. Different lasers have different transfer functions and the quality of lasers. There's a parameter called TDIG, extension ratio, how that affects the link performance. So these are the parameters with respect to laser, directly modulated laser, externally modulated laser, and vertical cavity laser, VCSEL laser. All this needs to be modeled for different links and types of fiber. They attenuate signal differently, and the different diode types based on different process nodes degrade the signal differently. So now we are talking about this complicated problem where the whole link needs to be simulated and ensured that they're operable together. So that's the challenge industry is trying to solve. And from OIF linear specification, there are new test points for interoperability which are proposed. So this ensures that multiple vendors can provide their solutions and that will work together. But very active place, and it eliminates the number of interconnects and save power for the data center. So that's a mega trend we are seeing. So that was one part of electro-optical interface that we are seeing going through power optimization. And the second part is by bringing optics closer to compute. So here we are talking about instead of pluggable optics. So last deployment, what we saw, it's still pluggable. We are still talking about a pluggable module where you are just eliminating retime interface. But now the second option here to save power in electro-optical interface is to bring optics closer to compute. So this is the present pluggable implementation. This is a retimed interface that I'm showing. So there's one effort that goes on to reduce power here. But on top of that, the couple of other aspects that industry is trying to solve is bringing optics as close to compute possible. So traditionally compute is done here in, like, it could be an accelerator, it could be a switch, and then it will drive an optics here. So this is onboard optics. So COBO, Consortium of Onboard Optics, was trying to lead this effort. And then there's a lot of talk at NPO today, near packaged optics. And their argument is with near packaged optics, the channel loss for electrical is about 13 dB, and the power efficiency of this interconnect is significantly lower compared to VSR interconnect. So the numbers industry is throwing, all these numbers are from OIF. The total link power here in pluggable optics will be about 8 picojoule per bit. And if this kind of employment is done, you save power by 25%, it's 6 picojoule per bit. And the next generation here, which has a lot of challenge, but there's a lot of push from the industry to make progress in this aspect, is to integrate whole electrical aspects and also the optical aspects on a single package. So the challenges I was alluding to, the performance of the laser significantly depends on the temperature. And if you have an electrical die here, which typically operates at higher temperature because it dissipates so much power, it typically operates at 70 degrees C, the performance of laser will degrade significantly. But industry is trying to solve that problem. Another challenge industry sees here is interoperability, and there are a lot of market dynamics as well. So let's see this co-package optics picks up. So how would our data center top rack or top of the rack switch will look? So presently, if somebody has to make this top of the rack switch, there is a switch, which is a merchant silicon switch, which will come from one vendor. And there are, as I was saying, 32 modules that will come here. So just to take some numbers, right? Let's say switch is for 10 unit and optical module is priced at 5 unit. So optical module vendors have 5 into 32, which is 160 unit of market space to play around. And the switch guy has 10. But let's say co-packaged deployment picks up. There is no market for the module vendors. There's going to be only one switch and everything will go through the switch because everything is co-packaged. So the whole market for the module vendors will go away. So that's one point. And second is switch anyway is the most critical single point failure in the network. So as we were talking here, each packet has to pass through so many hops in here. So many servers and racks will be connected to switch. And now let's say there is no pluggable module. There's only one core packet switch. So this is a critical point of failure. Anything below this or anything which is connected here will not be serviceable. So those are the challenges which industry is still willing to address because of the power efficiency this implementation offers. So there's very strong case of implementing with power efficiency improvement. So what industry is showing is you can save more than 60% of power from pluggable to co-package. And also latency. The more number of hops you make, more clock and data recovery you have to do. So you're not only burning power, but you're also adding latency. And this latency, as we talked earlier, has direct implementation on the workload you can process. So there's a huge push in the industry to try out and make this co-packaged work. And there are different interfaces. I'm just showing XSR, but there is UCIe based implementation of co-packaged optics as well. And we'll talk about that in the next slide. But this just shows the electro-optical interface that it brings silicon and optics package together, and it saves not only allows network scaling, but also reduce system power and latency. It is important to make this comment. So this was all for Ethernet InfiniBand kind of packet protocol. And this is very new that even PCIe and in turn CXL is talking about starting those memory mapped IO kind of protocols over optics. So this again is not new. 2005, 2010, 2015, there were discussion at PCI SIG on making PCI over optics possible. But it's the first time that, and this is very fresh news, just beginning of this month, that a work group is formed, which will seek the industry feedback to develop this optical interconnect. And as we discussed previously about the difference between a packet-based Ethernet to a memory-mapped PCIe, there are a lot of protocol-related aspects that needs to be addressed. For example, I've just highlighted 2 points here, that there's a lot of retry buffer. In Ethernet, there is no retry buffer mechanism in the protocol. It's best effort. But PCIe, because it's used from a memory map, it has a retry buffer mechanism. The protocol talks about it. So how would this be implemented in optical link? Optical links have a longer transmit time. As we were talking when I made the comment that the speed of light is slow, 330 nanosecond, let's say. So if we were to store data for 330 nanosecond, you need huge set of buffers, retry buffer. So those things need to be addressed. Then PCIe has a link training mechanism where the link starts from 2.5 gig And there are a lot of outband signal. How those be implemented in optics will be a challenge. And from optical vendor side as well, the way these optical vendors implement their photonic dyes is they fine tune for 1 lambda implementation. But as I was alluding that for the link training, PCI has to start from Gen 1, which is 2.5 gig, and then let's say to negotiate the speed up to 128 gig. So this optical dye vendor has to design in such a way that it works for 2.5 gig to 1.128 gig in the same set of fiber, in the same set of retry buffer. So those are the challenge at very high level. Just wanted to make, but this again will provide a low latency deployment. So there's a serious interest, and this again will save a lot of power because if PCIe or optics is deployed, I'll just want to show you that we burn power here when we go from PCIe to an Ethernet, and then we drive, let's say, DAC and optics. But let's say if PCIe over optics is feasible, if the industry comes up with a proposal, workable proposal, then we are saving power from all this intermediate reaches, right? So that will be really great power saver if in case that happens. And it's very happening to see that PCI SIG has started looking into it. So this is my last slide before we go to die, and this shows the technology roadmap. I mean, this is just to make very high level point that there has been relentless innovation. That pre 2020, it was all pluggable. And I was just very briefly made the point that QSFP 28. So this is one pluggable form factor up to 100 gig throughput. So it could be called 100 gig port because it's a quad small form factor, and 28 gig is line rate. So total 4 into 28 is about 100 gig. So this is a module. You can see how short it is compared to other previous generation module. And you can burn the DSP power in the same module because we have advanced CMOS process node that takes lower power for digital computation. Previous generation, coherent was always possible in CFP, this kind of huge bulky modules with the heat sink on. But with the advancement of both optical and CMOS technology, now it's possible to have 100 gig and even 800 gig today and this just shows pre-2020 in a pluggable form factor. And these are the technologies now we are trying, which is showing the performance improvement using integrated photonics, meaning using integrating multiple photonic functions like TIA, lasers in silicon so that you can do same package integration. So that's the next wave of productivity enhancement. And finally, again, these two are from OIF that people are talking about co-package, that the electrical dies will do all the switching. And this is laser, which is coming to the same package. And people are trying to address these problems of heat sink and the other non-realistic. And that's the final. We'll have optical links, multiple chips. So that's future. And this just shows what different tools and technologies we need to take this innovation forward. So you need photonic device tool so that these functions can be modeled correctly. Designing in a photonic foundry is very different from designing for a CMOS foundry. CMOS has a very well-developed process development kit and PDK, but a lot of photonics foundry still work based on MATLAB models. So we need better quality tools to model the photonic performance. Then layout synthesis, because photonic is more of an artwork and how that is extracted. So all these different waves of productivity, DRC and LVS and multi-die simulation is needed. But there's a lot of work the whole industry is doing in all these aspects to make it possible. Now let's look into die-to-die interface. So why die-to-die link are of interest? I set this up already that the shorter the links, lower the power, lower the losses. And from electro-optical point of view as well, I made the comment that photonic is showing more promise, photonic processes showing more progress that can be integrated, and process technologies are also showing progress that in one substrate, this multiple dies can be integrated together. So that's the context. Now let's look into specific implementation. So for the die-to-die, the biggest interest we have seen. So this shows the deployment, this is our own Synopsys data, which we are making public, that 57% of the deployment we see for die-to-die links of interest are to scale processing SoCs. So multiple accelerators and compute engines are joined together in single package to make multi-die. So this has been done from 2013, 14. It's a public news that Apple does it, AMD has done, NVIDIA has done. So this is most well understood implementation. And further on that, we have tried to divide the type of die-to-die link they use. So serial, which uses SerDes and takes slightly more power, is sort of 56%. And parallel, although it started very recently, is picking up. And 44% of this kind of die-to-die splitting to provide more compute facility in one package is going through parallel. Second important use case of die-to-die, which is 26% of total deployment, is for aggregating function. So this is, we talked about co-packaged optics, which is for data center, but there's also this base station deployment where you have MIMO, multiple input, multiple output, antennas for 5G base station, where you have a very high data rate JESD or CPRI protocol that is now going for die-to-die. So JESD 204D, which is the latest version up to 116 Gbps, can support die-to-die functionality. So that analog front end will be one die, and the base band in those kind of MIMO application will be another die. So there will be a deployment with that. So those are the second aggregating function for co-packaged. We talked about that. And the third is splitting large SoC. So this is well known that the manufacturability goes down if your die grows bigger. So in a wafer, if you're manufacturing only one die, so if there's only one fault in that manufacturing process, whole wafer is not usable. There are few digital technologies which allow you to correct, but still to make our case, right? Empirically, as the die size grows larger, the yield goes down. So if you split large SoC across multiple die, you can improve your cost and the yield. These are very significant saving. So we are seeing a lot of the split die deployment for just large functionality. So a lot of people have talked that the next generation 102 terabit switch will also be a multi-die implementation. So that's what we are seeing. And finally, this is disaggregating IOs. So this reduces the cost. So the argument here is if all the switching functions which can leverage the advanced process node switch to one very advanced process node, let's say 3 nanometer, the other IO functions which don't provide as much power efficiency as switching functions can still stay in more mature process node. So this kind of deployment, which we call disaggregating IOs or also seeing deployment, this is driven by cost equations for this deployment, that all the switching function goes to advanced process node and all the IO function goes to the previous generation process node. So all these four driving forces are leading to die-to-die deployment. So what makes this possible now, which was probably not possible, let's say 15 years or 10 years ago, is the advancement in the die-to-die packaging technology. And this is a very high-level plot to make the case that the two important parameters in die-to-die links are IO density, meaning the number of IOs you can integrate a package with respect to cost. So let's start from the present deployment or the most low-cost deployment, which is a organic substrate. So this green color substrate is called organic substrate. It's implemented using ABF, and there was shortage of it during COVID. But that's the most common deployment, that in a single chip or single package, you have one die which drives another die using this organic substrate. So this is the XSR application space we are talking about. So here we are talking about 1.5 picojoule per bit power efficiency for 112 Gbps, and the losses are about 10 dB. And you can see even the DRAM or the HBM type version, there are different types of DRAM that can be integrated this way, are in this organic substrate. So this is the lowest cost solution, But here, the line space, meaning the distance between two bumps or two parallel lines, is 10 micrometers. So the number of bumps you can add here are limited. And that's the drawback of this. But as technology moved forward, there are different technologies and different foundries or OSATs or bumping house came up with different technology. One I'm just showing here is called redistribution layer fan out. So on packaging terms, there is a metal layer which is very thick, which is thicker than anything else you can use in a die, which can be used to connect multiple dies. So as you see here, substrate is still here, different dies are there, but through RDL layers, we are connecting multiple dies. So this is an innovation that packaging houses have started offering, and this gives an improvement in lie space, meaning multiple bumps can be added. So you're increasing throughput here. And this is still possible with 56 Gbps. And again, it goes through SerDes. So there are different versions of it by different foundry. Info is something I can call out in wafer fan out. Then there is CoWoS, which is chip on wafer on substrate. There are different technologies which are providing this very high level 2.5D integration. So another way of this 2.5D integration is through interposer die. So this will be another CMOS die. So this die 1, die 2, which will have advanced computing facilities, will be in, let's say, 3 nanometer, 5 nanometer, but this interposer die could be in 65 nanometer or let's say 40 nanometer. And all this die will do is to route multiple signals between the dies. So this is another clever way of doing multi-die connection. And here, as you can see, the line space between different bumps can be reduced. So you can have multiple of these lines connected together. So this is called 2.5D because there's another dimension here. So there's 1D, 2D, and there's the interposer die. But the work gets increased that somebody has to design, manufacture, and then integrate this interposer. But you can see that substrate routing is reduced significantly. Most of the connection, multi-die connections are done using interposer. So that's a interesting implementation we have seen. And finally, this is a 3D stacking kind of deployment where we are seeing die 1 is actually placed face down on die 2. So the electrical channel is virtually non-existent. So they are driving this on top of each other. So you can add multiple bumps here, and this could be even bumpless connection based on the deployment. So this saves a lot of power. It's called 3D, but it's most expensive, and the manufacturability ensuring here it's very expensive. So if there's no standardization from the industry, every foundry will offer their own different ways of deploying, and it will be difficult to ensure interoperability among different vendors, different packaging house, different functions. So for that, there are different standards that define interfaces for this kind of die-to-die technology. At very high level, we can classify the two different classes of die-to-die. So one is parallel. Here, the clock is routed separately and multiple lines will just have data. So there is no CDR or clock or data recovery in the receiver, which I was trying to highlight takes a lot of power. And these kind of interfaces typically use NRZ modulation because it becomes really difficult to actually align this clock with all this data and recover data in PAM4 fashion. So this is DDR-like. Industry has been doing it for a long time. Dual data rate, where on both rising and falling edge of clock, you have data and clock is sent differently. So the parallel solution, the industry has multiple options, and I'll show those options in the next slide. And the serial option, this we have been talking about, that OIF has talked about 112 gig XSR, 56 gig SSR. Here you just have a TX plus, TX minus, RX plus, RX minus, 4 pins and very high speed data you can transfer. But here you have to implement a clock and data recovery, and the power efficiency is about 1.5 picojoule per bit. And parallel, people have been talking about 0.3 picojoule per bit power efficiency. So we are talking about 80% power reduction if you go from serial to parallel. That has made industry really interested in looking at this kind of interconnect. So this slide shows the different standard bodies and alliances. that are drafting standards for the interoperability among different die-to-die implementation and their technical merits and maturity and the strength of ecosystem. So this we have been talking about. So the OIF Optical Interconnect Forum, they have standard XSR. They have talked about, they have defined 112G with 10 dB loss. They are defining 224 gig data rate now. So what's on top of protocol here? So that is not defined. We made this point earlier that OIF defines the electrical channels and the protocols are defined by other. For example, you can run Ethernet, InfiniBand. So this is not defined here. And as this is high power, so the focus is 2D package, which is the lowest cost. So if I'm making an optical substrate and I'm burning power here, I'll better use a low cost package substrate. So its packaging focus is 2D and its target application is optical networking, die-to-die splitting, and so on and so forth. We talked about that. Now let's look at different other attempts that standard bodies have made. So Open Compute Project is also an open platform where a lot of hyperscalers discuss the architecture and share the latest problem and come up with a solution. So they have come up with two different standards. BOW is bunch of wire and OHBI is open high bandwidth interface. And they talked about per pin data rate of 8 gig or 16 gig. And again, these are protocol layers are not defined, and they were focusing on different kind of package layer. And chip alliances had different data rate, and that this also did not pick up as much. Things changed significantly last year when the whole industry body came up with Universal Chiplet Interconnect Express. The name is very similar to PCIe, Peripheral Component Interconnect Express. And 22 years back, PCIe also solved the same problem. When PCIe came, there were so many different interfaces. There was SATA, there was ATA, Advanced Technology Attachment. There were for GPUs, there were different accelerator, and all those were replaced by PCIe. And the idea was there was a protocol stack on top of that, a layer 2 that can be used to write software. And no matter what file you use, your software remains same across generation. So UCIe does that effort now. I'll talk more about this part there. And the flexibility they are providing is they're not proposing one protocol. So for example, PCIe has some overhead. CXL, I talked the beautiful thing it does for memory pooling. So you can run CXL on top of this. In addition to that, they have talked about a streaming protocol, which is ultra lightweight. So which will be equivalent to just raw data transfer. So it's future proof and there are different kind of protocol that can run here. And it's future proof with respect to focus as well. So it call it standard package and it also defines an advanced package. Anything 2.5D to even 3D is advanced package. So no matter how process technology scales, the same software you have written for previous generation can be used for the next generation. So that's the flexibility UCI offers. And it's targeting all the applications. So we are seeing optical deployment. We are also seeing scaling and memory pooling with HBM memory, so on and so forth. So this is seen as a really universal interconnect express. So it's most comprehensive standard, defines all use cases and packaging type. And I'll show in the next slide, they have 100 plus members and they have system vendors here like hyperscalers, CPUs vendors, foundry, and OSAT, which is outsourced semiconductor assembly and test. So all of those are part of the standard. They're coming together, talking about interoperability, and its objective is to unify the interface and ecosystem. So this is the work that UCI is trying to do and how it solves industry problem. So this is the physical layer or the electrical interface we have been talking. Now this will be a parallel interface and they have defined the electrical and also the sideband signal. A lot of time to do the link training, there are some sideband signals which are needed. So those are also standard defined. And there is this interface, RDI, raw data interface. This is defined between two logical separated layers. So this will be just a PHY, and there's a raw data interface. So you have different ways of implementing it at different clock rates. And then there's a die-to-die adapter based on the protocol implementer wants to run. Let's say you are using this die-to-die interface only for scaling. You don't need to have full-fledged PCIe protocol. In that case, you just have die-to-die adapter. And for very lightweight FEC, they have flit data interface. So this again is a set boundary between this logical layer and the next protocol layer. So this ensures that the same physical layer can be leveraged to implement different kinds of link. You can just implement a raw data link where you just do data transfer between accelerator and the GPU. And then you can use just the flit data interface where you can increase your channel loss a bit more and you have this forward error correction. Or finally, you can run the full-fledged the CXL or PCIe. You can make one single package which will have multiple dies and you can run whole PCIe software, CXL, and also streaming and goes up to cache coherency as well, the CXS layers as well. So this way, because there are clear boundaries here, you can get silicon maturity of 1 phi, and then you can use a different logical layer. You can run different protocol. So that's the solution UCI offers today. It's a lightweight die-to-die interface, and it provides something for everybody. If you're just running raw streaming mode, you get this option. And if you're running whole PCIe, you get another option. It enables multi-generation software interoperability. So this was the point I was trying to make. As this protocol layer will be a large bunch of RTL, and you would design a software based on that RTL, you can change the lower layers in the next generation, and your software doesn't need to change because these interfaces will remain constant and are standardized. It allows heterogeneous integrated packages because this physical layer is not bound with one specific technology or one specific implementation. You can have one physical layer, let's say in 3 nanometer, and you can have another in 12 nanometer. So it truly allows heterogeneous integration packages. It supports for all packages technology for the same PHY architecture because the channels are defined in such a way that they are not tied to one process technology or one application. It allows integration of not only electrical die, but also electro-optical die. And I was mentioning that analog front end, which are RF processes as well. So it supports all packaging technology. It supports different protocol. Streaming as well is the one where you just want to stream some data from one die to another. And the cache coherency, there are different protocols that can be done on top of that. So why this is preferred today, and why I'm talking about this in the hot interconnect and interconnect. So the reason for this is the industry has come together. This shows all the members. This is not the latest list, but it's a true representation that shows we have hyperscalers here. We have the chip manufacturer here, interconnect guys here, and we have Synopsys as well. Everybody's sitting together and people are marching towards making these PPAs possible. So there's a huge push, and this will have overall saving in powers of data center and the throughput because latency will go down. So everybody is marching towards getting energy efficiency of 0.3 picojoule per bit. So this will be massive, massive compared to the XSR interface, which is 1.5 to 1.8 picojoule per bit. Edge efficiency, meaning the throughput you can have from one die to another, is also really significant. It's 5 terabit per second for per millimeter. So if this is your die, per millimeter of your die, you can pump in and out 5 terabit per second. So it provides significant edge efficiency. And the latency is just 2 nanoseconds. So it will enable a lot of complex processing workloads, with large language models. So this is truly enabling the hyperscale data centers to implement a solution which will not be bogged down with the memory wall, and it provides the throughput they need to process the machine learning algorithms. I think I talked about these points earlier, all use cases, package type. So the point I was trying to make is everybody is sitting together and trying to do the ecosystem interoperability. And it's not linked to the first generation deployment of just the standard. People are talking about a true chiplet marketplace, which will take place in about, let's say, 26, 27, where you can get a chiplet. Chiplet is a die. It's not a full chip. It's a small form of chip. That's why chiplet, like cigarette. So you can take multiple chiplets from multiple vendors and you can make your package together. So that's the end goal where this driving towards. And that will be so power efficient because all of these vendors have committed to some goals with respect to power and also the latency. So there's a true democratization and interoperable ecosystem for a shortest channel across not only electrical but electro-optical die. So that's the vision people are marching towards. And because in this presentation, I was trying to highlight EO interfaces as well. So I thought it's a good summary slide how would EO interfaces will look with the UCIe. So there are different options people are trying and they have different advantages. So this would look similar to what we talked about XSR and optical module earlier, that the compute die can now be integrated in the same package with the optical die, and there could be an electrical die which will do the UCI conversion and then will implement the DSP portion here for the optics. So this will be a sort of 3-die system, and this will ensure multiple optical dies can be integrated. So this could be, let's say, 100 gig lambda, 200 gig lambda. You can have one electrical die which can do different DSPs to drive all of that. So this 3-die implementation with the UCI interface will allow true multi-vendor interoperability, that you can get this from one vendor, this from another vendor, and this will work. Laser integration is still a holy grail. I'm not making any comment there, showing this is an option. If we reach there, that's really good. Robust interoperability as cost of slightly higher power. So there are two UCI PHYs here, you would see 0.3 picojoule, 0.3 picojoule. So it's still slightly higher power. So another 2-die implementation could be where on the other side, in the optical die itself, the designers terminate this UCI receive and transmit signal through the analog front-end design. So this will save power of another UCI design, and it will save designing UCI PHY in those complicated optical processes I was highlighting, which generally don't have such robust PDK for such complex analog design. So that's another option that industry is trying. And here the compute die, which will be advanced CMOS process node, will have this optical DSP based on the optics which will be implemented here. So this is a true die implementation, which is still, I would say, some custom because you are tied down to the interoperability of these two, but it saves significant power as it eliminates another die. So those are the two trends we are seeing as future electro-optical interfaces when it goes to die. And this is my final slide about summary and conclusion. So what's now and what's next? So we talked about CXL-based memory pooling technology. So this addresses the memory wall or low latency problem for the next generation machine learning workload, large language model, which has billions and trillions of parameters. The new power efficient and low latency electro-optical interfaces as linear, and in linear, we have taken off the CDR or retiming function. We are not adding latency, we're not adding power. So that's another trend we are seeing. And this mega trend of die-to-die interconnect with the standardization of UCIe, which will enable this multi-form factor integration, is the next throughput improvement for new frontier of processing efficiency is what we are seeing. And the convergence of these technology will offer the new avenues for optimizing system performance, where we will not only be able to save the power, but also will increase the system throughput. So I'm really thankful to my colleagues at Synopsys, Dr. Manuel Mota and Mr. Manmeet Walia and Dr. Al Shawal. And I thank you so much for your patient hearing. It was a long tutorial, and I really appreciate you being with me. I'll be happy to take questions.
Thank you very much, Priyank. A big virtual round of applause to you. That was a fantastic tutorial. You covered so much ground from the very fundamental beginnings to some pretty advanced topics, and I really appreciate it. I think it's an excellent fit for what we're looking for in hot interconnect tutorials. We do have one question in the Zoom chat. I'll just read it out in case folks are not able to see it. And this is a good one. Is linear drive 3D CPO being considered in future standards? Advanced packaging will enable 3D stacked ASIC on top of active optical interposers, eliminating the need for XSR retimer in the optics.
Right. So present focus for linear is for pluggable and NPO is what we are seeing today. That's 2023. But they're committed that through UCIe, this conversation will probably start next year or so, but it's happening in a confined manner, meaning there is no talk of interoperability, but we are seeing the closed door deployments of such interfaces as that will save a lot of power. So from the industry overall, the present focus is for pluggable and NPO. For the UCIe 3D stack, there are a few deployments which are in closed door today, but they would come to open ecosystem maybe in a year or two.
Okay, great. We just have a new question on the Slack channel. In current data centers, do you know what percentage of the power is dissipated by I/O transfers alone?
Right. So this is our internal Synopsys estimate based on the things we are seeing. And we have, I mean, I would say my team has pegged it to 27% power. I spent a lot of times finding public information. So it's very difficult to find and it varies a lot. So this is our internal based on the power and other things.
Right, and I was interested in that 27%. That's from your experience. You came up with that measurement.
Correct. So we
Yeah.
have visibility into the power, which is in switch, which is an optical module, which is an accelerator, which is in processor. And out of that, based on total compute and total this, so compute comes around 20% and
Mm-hmm.
interconnect comes around 27%.
Yeah, and is there anything you can say, roughly speaking, about if that number is consistent across Ethernet, InfiniBand, and alternatives?
It
Or,
will be, yeah, it will
yeah,
be consistent.
yeah.
And at OIF, there are other system vendors who have made similar claims as well. Cisco has made something available
Mm-hmm.
which aligns with this.
Interesting. I guess we have a little bit of time, and I have a few far less advanced questions, if that's okay.
But I'll just
This is
make one request to anybody who has
Yeah,
listened, right? If you're a
yeah.
designer, just try to save 1 picojoule of power. You will save hundreds of megawatt and make this world a lot greener. So as a design engineer, right, we don't think about that. That if I do a bit more optimization in my SerDes or in my optics, I can save so much of power.
Yeah, great point. So yeah, like I said, I just have a very high level sort of newbie question about you're talking about co-packaging optics being, driven in OIF, right? But it's kind of tentative and they're working it out. And it sounds like maybe discrepancies in operating temperature between the chip and the laser is a big challenge there. So can you say a little about like what efforts are going on there and what it's all this talk about the history of these connectors has gotten me interested in whether or not operating temperature is standardized and what's the history with things like that challenge.
It's going full steam. Actually, last OFC conference, optical fiber conference, which happens in San Diego in March, which is the best industry event, Broadcom showed this demo. And OIF has standardized 3.2 terabit optical module, which is co-packaged. So they have demonstrated it that it's possible. So the laser was still external, that was not in the same package, but that was a co-packaged electrical and optical integration that has been demonstrated. And there is work which is currently going both in closed door and also in open forum that is seeing how laser can be integrated and manufacturability can be ensured. So a lot of contribution, and you would see closed door deployment first than in open standards, but that's happening.
Yeah, interesting. Let's see if we have any other questions coming in. Not yet. Just a comment that it's agreed. It's a great talk. Let's check Zoom chat. I'm not seeing anything. So I had a thought or question about CXL, and I think it could just be my ignorance on the topic. But I have been excited for CXL because I think it has powerful implications. I'm more of a software guy. for programming models where, say, expanded coherency domains have sort of fantastic implications for ease of programming. But it seemed like your talk kind of focused as well on how it addresses the memory wall problem, and it almost sounded like your tone was very optimistic that it might actually fix the issue, right? And I'm trying to wrap my head around that, because my understanding of it is that it, there's still a cost of, say, implicitly, transferring across coherence domains, that you're just CXL kind of hides that from the programmer and enables like a flat memory space. Am I missing something there? How does it how would it fix the memory wall problem?
So there are two very recent paper. I think Microsoft published this the beginning of this month. They analyze their data center traffic and they have these different models and they have modeled the latency of CXL as well. So they have made an assumption that CXL, RX, and TX latency, let's say it's 25, how many hits and misses they would see to execute one workload. So they have quantified that information. So they have given this public data points in the beginning of this month, and I can reference that paper here, which makes that now software designer can have one contiguous set of memory and which will be comparable to L3 cache, and that would sit through another accelerator. And they have provided something that's public information. And there's another hyperscaler, I forgot it was Meta or Microsoft, but they also concurred.
Yeah, that's great. I'd love to see that paper. If you want to IM it to me, I'd very much appreciate that.
Yes.
Okay, so I think that gives us a few minutes to get ready for the next tutorial. Again, thank you so much, Priyank. That was, from my point of view, the perfect hot eye tutorial to lead us off today. So much coverage. I learned so much. I hope that's the case for everyone else. Again, a big virtual round of applause to you. Thank you. And yeah, if anyone has any other questions, please put them in the Slack chat channel. And I think I will move over the questions that we had in Zoom, because they'll just get lost to the Slack channel just for posterity.
Thank you so much, everybody, for listening to me for 2 hours and 30 minutes. I appreciate your patience.
It was a quick 2 hours. Yeah.
Thank
Thanks
you
very much.